Section: Scaling by Thinking in Continuous Space. In this section, we discuss how humans naturally invest varying amounts of mental effort into different problems. While we can think over extended periods by verbalizing and writing down our thoughts, much of our cognitive processing occurs through complex patterns in the brain before we articulate an answer. Early efforts to enhance language models focused on increasing their size, which demands vast amounts of data and computation. Recently, we have seen researchers looking into improving models' reasoning abilities by scaling the computation during testing. The common method involves training models on long examples to help them verbalize intermediate steps, but this can seem inefficient since it reduces complex reasoning to a single verbal output. We believe that models could perform better if they could think in their continuous latent space. To tap into this potential, we propose adding a recurrent unit to the model. This unit processes and updates its hidden state in a loop, allowing for ongoing computations. Although this approach isn't the most common yet, it has been a recurring concept in machine learning, appearing in various forms like recurrent neural networks and loop transformers. Our research demonstrates that depth recurrent language models can learn effectively, be trained efficiently, and show significant performance gains when we scale test time computation. Our transformer architecture includes a latent depth recurrent block that runs for a randomly chosen number of iterations during training. We find that this method can scale to billions of parameters and over 500 billion tokens of pre-training data. During testing, the model enhances its performance through recurrent reasoning in latent space, allowing it to compete with other models that have more parameters and training data. Moreover, we show that recurrent depth models naturally support features at inference time that require extensive tuning in non-recurrent models, such as adaptive compute per token and speculative decoding. We conclude our study by tracking token movements in latent space, revealing interesting computational behaviors that emerge with scale, like the model rotating shapes for numerical tasks. We explore why we should train models with recurrent depth. Recurrent layers allow a transformer model to perform numerous computations before producing a token, offering a straightforward way to scale computation during testing. Compared to traditional long context reasoning, latent recurrent thinking has several benefits. It doesn't need specially crafted training data, as our models can train with a flexible compute budget using standard data. They can also improve their performance at test time with additional compute. Furthermore, latent reasoning models require less memory than chain-of-thought models, which need long context windows and specialized training methods. Recurrent depth networks perform more operations per parameter than standard transformers, reducing communication costs between devices during training, especially with slower connections. By creating a compute-intensive architecture with fewer parameters, we aim to encourage models that solve problems through thinking, learning strategies, logic, and abstraction rather than mere memorization. The effectiveness of recurrent methods for learning complex algorithms has been shown in the literature on deep thinking. Philosophically, we hope that latent reasoning captures aspects of human reasoning that are hard to verbalize, like spatial thinking and physical intuition. Through many iterations in a high-dimensional space, we can explore multiple directions at once, leading to systems capable of complex reasoning. We argue that scaling computation in this way complements other scaling methods, such as extended verbal inference and increasing parameter counts during pre-training, potentially creating a new dimension for enhancing model performance. Section Summary. In this section, we explore the advantages of using recurrent depth in language models, which allows for more efficient reasoning by enabling the model to perform multiple computations before generating a response. We argue that this approach not only reduces the need for specialized training data but also enhances performance through latent reasoning, ultimately leading to models that can exhibit complex reasoning behaviors akin to human thought processes. Section: A Scalable Recurrent Architecture. In this section, we will outline our proposed architecture for a transformer that incorporates latent recurrent depth. We will discuss our design choices and conduct small-scale tests. A diagram of our architecture is available in the referenced figure. We denote the sequence dimension as n, the model's hidden dimension as h, and its vocabulary as the set V. Our model is mainly built around decoder-only transformer blocks, which we organize into three functional groups. The prelude, P, which transforms the input data into a latent space using several transformer layers. The core recurrent block, R, which is the main unit for recurrent computation that modifies states. And the coda, C, which converts the latent space back into output using multiple layers and includes the model's prediction head. The core block is positioned between the prelude and coda, allowing us to loop it and create an indefinite number of iterations. Given a certain number of recurrent iterations, R, and a sequence of input tokens, these groups work together to generate output probabilities. Starting with an initial random state, the model repeatedly applies the core block, which takes the previous latent state and the embedded input to produce a new latent state. After completing all iterations, the coda block processes the final state to generate the probabilities for the next token. This design is inspired by research indicating that injecting latent inputs at each step stabilizes the recurrence and helps achieve a steady state, regardless of how we start. This recurrent setup is essential for learning stable iterative processes. For instance, in gradient descent, we begin with a random state and repeatedly apply a simple operation based on the previous state and the data. We also inject data at every step in our architecture. If we only provided the data at the beginning, the iterative process would become unstable, as it would depend solely on the initial conditions. Our approach to embedding input tokens into a hidden latent space is based on empirical findings that show the initial and final layers of large language models differ significantly, while the middle layers are interchangeable. We also note that our iterative architecture resembles modern diffusion models, particularly latent diffusion models. We experimented with variations similar to diffusion models but found that adding noise did not improve our results, possibly due to our training objectives. In terms of microscopic design, we adhere to standard transformer layer structures within each group. Each block consists of multiple layers, including a causal self-attention block and a gated activation function. We utilize RMS norm for normalization and include learnable biases only on queries and keys. To stabilize the recurrence, we arrange the layers in a specific format, which we found necessary for training at scale. The prelude block first embeds input tokens and then applies several prelude layers. Our core recurrent block begins with an adapter matrix that maps the concatenated latent state and embedded input into the hidden dimension. We discovered that concatenation works best for larger models. The output from the core block is then normalized before being processed by the coda, which also includes normalization and projects into the vocabulary. In summary, we can describe our architecture by the number of layers in each stage and the number of recurrences, which can vary with each forward pass. We train several small-scale models and one larger model, which, despite having only a few real layers, can effectively reach a much greater depth through recurrent iterations. Section Summary. In this section, we propose a scalable transformer architecture with latent recurrent depth, structured into three functional groups: a prelude for embedding input data, a core recurrent block for iterative state modification, and a coda for output generation. Our design emphasizes stability and convergence through repeated data injection and a specific layer arrangement, allowing for effective computation chains that exceed the depth of traditional fixed-depth transformers. Section: Training Objective. In this section, we outline our training objective and methodology for recurrent models. To prepare the model for functioning with increased recurrent iterations during testing, we randomly select the number of iterations for each input sequence during training. We aim to optimize the expected loss over random samples from our data distribution and random iteration counts from a specific distribution. We denote the model output as M, and the shifted sequence as X prime, which represents the next tokens in the sequence. We choose a log-normal Poisson distribution for our iteration counts, targeting a mean recurrence and setting a variance. This distribution typically samples values below the mean but also allows for occasional higher counts. To manage computation and memory efficiently during training, we only backpropagate through the last few iterations of the recurrent unit. This approach allows us to work with the heavy-tailed Poisson distribution without increasing memory usage based on the number of iterations. We fix the number of iterations to 8 in our main experiments, which maintains consistent memory usage. After confirming that we can train smaller models effectively, we proceed to larger-scale training. Given our limited computational resources, we decide to focus on training a single medium-scale model rather than multiple smaller ones. We detail our training setup, which includes the architecture, optimization methods, and pre-training data. We will publicly share all training data, code, and some intermediate model checkpoints. For our pre-training data, we select a mixture that encourages emergent reasoning behaviors rather than just optimal benchmark performance. Our dataset is primarily focused on code and mathematical reasoning, supplemented with enough general web text to develop standard language modeling skills. We also incorporate relevant instruction data into the pre-training mix, although time constraints prevented us from optimizing this mixture further. Regarding tokenization, we create a vocabulary of 65,536 tokens using byte pair encoding, specifically tailored to our instruction data to enhance efficiency. We modify the pre-tokenization process to better accommodate code and other specific formats. Each document begins with a special token, and we pack our tokenized documents into sequences of 4,096 tokens, ensuring we address the grounding problem by discarding incomplete document ends. In terms of architecture, we scale our model by adjusting the number of layers and increasing the hidden size, resulting in a model with approximately 1.5 billion parameters in various components. We apply a specific initialization method for larger scales, using a truncated normal distribution for most parameters while ensuring the output layers are initialized with smaller values. The embedding layer output is scaled appropriately, and we also sample the initial state from a truncated normal distribution. Section Summary. In this section, we describe our training approach for recurrent models, which involves randomly sampling iteration counts during training to optimize the expected loss while managing memory through truncated backpropagation. We also outline our large-scale training setup, focusing on a dataset mixture aimed at enhancing emergent reasoning behaviors, and detail our architecture and initialization strategies for the model. Section: Locked Step Sampling. In this section, we discuss our approach to locked step sampling, which allows us to synchronize parallel workers by sampling a single depth for each micro-batch of training. This synchronization prevents workers from idling while waiting for the one with the largest depth to finish its backward pass. We found that this adjustment enhances compute utilization without slowing down convergence. However, with larger batch sizes, we could further optimize training by sampling and scheduling independent steps for each worker to better reflect the expected steps in our loss function. For our optimizer and learning rate schedule, we utilize the Atom optimizer with decoupled weight regularization, setting specific parameters for beta values and learning rate. We implemented gradient clipping for values above 1 and employed a warm-up phase to reach our maximum learning rate within the first 4,096 training steps. Regarding our compute setup, we trained our model on the Oak Ridge National Labs Frontier Cluster, which features a large-scale HPE Cray system with multiple AMD GPU nodes connected through high-speed NICs. We used a PyTorch-based implementation in mixed precision. In terms of device speed and parallelization, each MI250X chip can achieve significant performance, and we measured a maximum speed of 125 TFLOPS for matrix multiplication. Our optimized implementation reached a training speed of 108.75 TFLOPS on a single node. Due to our model's design, we managed to train it using only data parallelism, minimizing inter-GPU communication. When scaling to 4,096 GPUs, we achieved a global batch size of 16 million tokens per step, with a notable throughput of 1 to 1.2 million tokens per second. Our training timeline consisted of 21 segments, each lasting up to 12 hours, primarily scheduled in early December 2024. We also conducted a baseline comparison with a simpler feed-forward training setup. Ultimately, we pre-trained our main model on 795 billion tokens, taking advantage of our constant learning rate schedule to add segments as resources became available. We also learned about the importance of normalization strategies and initializations at scale. While smaller scales showed minimal differences, our first large-scale training run stalled due to an initialization issue that caused the model's representation to collapse. We addressed this by adjusting our normalization and embedding scale, which initially seemed to help but later led to a local minimum. In our final run, we reverted to a more effective configuration, which allowed us to train smoothly for 750 billion tokens without significant interruptions. We refer to the final checkpoint of this successful run as our main model, named HUGINN0125. Section Summary. In this section, we describe our approach to locked-step sampling for synchronized training across parallel workers, which enhances compute utilization without affecting convergence speed. We also detail our training setup using the Atom Optimizer, mixed precision on a large-scale AMD cluster, and the importance of proper normalization and initialization strategies at scale to prevent model collapse during training. Section: Benchmark Results. In this section, we present our benchmark results. We trained our final model on 800 billion tokens and a non-recurrent baseline on 180 billion tokens. We evaluated these models against other open-source models that were trained on similar public datasets, including Amber, Pythia, and various Olmo versions. We used standard benchmarks through the LM-eval harness and coding benchmarks via Big Code Bench. When comparing our model to other large language models, we found it challenging due to the variations in the fixed-depth transformer architecture. Our model has 3.5 billion parameters, which means it requires less bandwidth during pre-training, but it processes a similar amount of raw computing operations as a 32 billion parameter transformer. It can also improve performance with increased computing resources, up to levels typical for a 50 billion parameter model. We should note some limitations in our training run. Our main checkpoint was trained for only 47,000 steps on a mixture of data that hasn't been extensively tested, and we did not reduce the learning rate from its peak. While our token count is large compared to older models like Pythia, it is small compared to modern efforts like Olmo and much smaller than datasets used for industrial models. Despite these disclaimers, we gathered results for established benchmark tasks and presented them side by side. Our model outperformed the older Pythia series and was comparable to the first generation of Olmo, but it lagged behind later Olmo models that were trained on larger, more curated datasets. Given the limitations of our training run, we find these results promising and suggest further research into latent recurrence for test time scaling. We also evaluated our model on math and coding tasks. For math, we used benchmarks like GSM-8K, Math, and MathQA. In coding, we assessed MBPP and human eval. Our model significantly outperformed all others except the latest Olmo 2 in mathematical reasoning. In coding benchmarks, it surpassed all general-purpose open-source models, though it did not outperform specialized models like StarCoder 2, which were trained on trillions of tokens. We observed that while improvements in language modeling are slowing down, advancements in code and mathematical reasoning continue steadily throughout training. We explored how much of our performance can be attributed to recurrence versus other factors like dataset and architecture. We compared our recurrent model to its non-recurrent counterpart, both trained to 180 billion tokens. The recurrent model showed a clear advantage, especially on more challenging tasks like the ARC challenge set. For simpler tasks requiring straightforward recall, both models performed similarly. Notably, the recurrent model was 5 times better than the baseline on GSM-8K early in the pre-training process. We found that when using only a single recurrence, the model's performance plateaued between the 180 billion and 800 billion checkpoints, indicating that improvements were tied to the recurrent block rather than the non-recurrent layers. We also examined the performance of our model in relation to the number of few-shot examples and recurrence. Without few-shot examples, the model's performance plateaued around 8 to 12 iterations. However, With more context, it could reason about additional information, saturating at around 20 iterations with one example and 32 iterations with 25 to 50 examples. This aligns with generalization improvements seen with recurrence. Additionally, when we re-evaluated OBQA without a closed book format and provided relevant facts, our recurrent model showed significant improvement, nearly closing the gap with OLMO 2. This makes sense, as recurrent models have less capacity for memorization but greater capacity for reasoning about context. Section Summary. In this section, we present benchmark results for our model trained on 800B tokens, comparing it to other open-source models like Amber and OLMO. Our findings indicate that while our model outperforms older models like Pythia and is competitive with OLMO 7B, it still lags behind later OLMO versions. We also observe significant improvements in mathematical reasoning and coding tasks, particularly highlighting the advantages of recurrence in handling complex challenges. Section: Improvements through weight averaging. In this section, we explore improvements through weight averaging. By maintaining a constant learning rate, we can enhance our results using weight averaging, which mimics a cooldown effect. We implement an exponential moving average starting from our last checkpoint, using a factor of 0.9 and incorporating the last 75 checkpoints with a dilation factor of 7. This adjustment to existing methods allows us to provide an EMMA model that boosts GMS 8K performance to 47.23% flexible and 38.59% strict when tested at a recurrence of 64. Next, we discuss how recurrent depth simplifies large language models, LLMs. These models not only improve performance in mathematical and coding tasks but also serve as effective tools for various methods that typically require more effort with standard transformers. We will give a brief overview of this in the following section. We also demonstrate zero-shot adaptive compute at test time. Our model can adjust its computation based on each query, operating in different recurrence modes. While the model is trained this way, it is more efficient to stop early when predictions are straightforward, focusing computational resources on more challenging decisions. Unlike other models that need specific training for early exits, we evaluate our model's ability to exit early using a simple criterion. If the difference between two successive steps is less than 0.0005, we stop and generate the next token. We illustrate this adaptive compute behavior, showing that the number of steps to exit varies by category, with the model exiting sooner on high school math questions compared to moral scenarios. Our preliminary tests on MT-Bench indicate that this adaptivity does not significantly affect performance in conversational benchmarks. We address a common concern regarding early exits in models with self-attention, which can disrupt key-value caching. When a token exits early, it may not have computed the necessary activations for previous tokens. Instead of recomputing all missing states, we utilize the most recent available key-value states in the cache, allowing the model to attend to the latest entries from previous tokens, even if they were computed at different depths. We also explore zero-shot KV cache sharing to enhance efficiency by reducing the memory used for the KV cache. Typically, transformers need to be trained from scratch for this feature, but we find that we can share KV caches in our model with minimal performance impact. We set a fixed budget for the KV cache at each token, overriding entries as needed. This approach can independently reduce memory usage or work alongside per-token adaptive compute without degrading performance. Additionally, we introduce zero-shot continuous chain of thought. Instead of starting with a random state for each generation step, we can begin with the last state from the previous token. This method reduces the average steps needed for convergence and allows the model to exit earlier by reusing previous computations, especially in tasks like philosophy questions. Lastly, we discuss zero-shot self-speculative decoding. Our recurrent depth models can generate text more efficiently through speculative decoding without needing a separate draft model. Unlike standard transformers that require external models for this process, our approach allows us to draft the next tokens with fewer iterations, which can later be verified with additional iterations. This method is efficient, as the states computed during drafting can be reused during verification. Section Summary. In this section, we describe improvements achieved through weight averaging, which enhances model performance, and introduce zero-shot adaptive compute that allows our model to efficiently adjust computation based on the difficulty of tasks. We also discuss techniques like zero-shot KV cache sharing and self-speculative decoding, which further optimize memory usage and generation efficiency without compromising performance. Section. What mechanisms emerge at scale in recurrent depth models? In this section, we explore what happens in latent space when our model recurs. To gain insights, we analyze the paths taken by the model in several examples, focusing on the patterns that emerge when we train at scale. Unlike previous studies that enforce a fixed point through their training objectives, we utilize a truncated unrolling approach. We present a chart showing the distance between each point in a trajectory and an approximate limit point, calculated over 128 iterations. The chart displays the sentences from top to bottom and the iterations from left to right, revealing that the convergence behavior varies based on context. We notice that crucial parts of the question and the beginning of the model's response are more thoroughly processed in latent space. Additionally, we observe different behaviors among identical tokens, indicating context sensitivity. It's important to note that the distance to the limit point does not always decrease steadily. For instance, in the case of school, the model may follow complex paths while processing information, even if this isn't explicitly stated in our training objective. We delve deeper into the trajectories of specific tokens, using a PCA decomposition to visualize their paths across the first 6 PCA directions. While many tokens settle at a fixed point, more challenging questions lead to orbit patterns in the trajectories. These multidimensional orbits may serve a similar function to periodic patterns seen in fixed-depth transformers used for arithmetic tasks, but we find that these patterns extend well beyond arithmetic in our model. We frequently observe orbits in tokens like makes or thinks, which shape the response structure. Moreover, we identify certain key tokens behaving like sliders, where the trajectory drifts in one direction, potentially allowing the model to count iterations. The structured trajectories in latent space provide insight into the model's computational processes. Instead of a straightforward reasoning chain, we see rich geometric patterns, including orbits and drifts, suggesting the model is learning to utilize the high-dimensional latent space for reasoning in innovative ways. We also confirm that our models exhibit path independence, meaning they follow similar trajectories regardless of starting points. This consistency is evident in the same orbital patterns and directional drifts that arise from different initializations. In terms of related work, the significance of recurrence in machine learning is substantial. Recurrence has been applied in transformers to model universal machines, and recent advancements have highlighted its benefits in learning generalizable algorithms. Other studies have examined depth recurrent transformers and their advantages through theoretical and small-scale analyses. Our approach differs from equilibrium and diffusion models, particularly in the training objective, where we propose truncated unrolling as a scalable alternative. Overall, architectures that recur in depth can be seen as learning the gradient of a latent energy-based model, linking them to test time adaptation. Additionally, there are various hybrid architectures that incorporate latent subnetworks or weight-sharing techniques. While we view recurrent depth as a natural method for reasoning in continuous latent space, other works discuss fine-tuning existing fixed-depth transformers to achieve similar capabilities. Section Summary. In this section, we analyze the latent space trajectories of our recurrent depth model to understand the emergent patterns during processing, revealing that the model exhibits complex behaviors such as orbits and drifts, which facilitate its reasoning capabilities. We also confirm that these trajectories maintain path independence, demonstrating consistent behavior across different initializations, and highlight the model's ability to leverage its high-dimensional latent space for computation beyond traditional sequential reasoning. Section: Future Work. In this section, we explore future work beyond our analysis of recurrent depth models. We recognize that there are many unanswered questions, such as the potential for new post-training methods that could enhance these models. For instance, we could consider fine-tuning to reduce recurrence or using reinforcement learning with data of varying difficulty levels. Additionally, we might look into incorporating reasoning from chain-of-thought data into the recurrence. We also note that we haven't addressed how our work relates to other advancements in model architecture. Efficient sequence mixing operations, particularly those that operate linearly with respect to sequence length, have limitations on the number of comparisons they can perform. However, with recurrent depth, we can repeat blocks with linear operators until all necessary comparisons among sequence elements are made. For simplicity, we have concentrated on a single recurrence, while previous studies have examined multiple recurrent stages. Furthermore, our proposed architecture is designed to be compute-intensive, featuring more materialized parameters than actual parameters, similar to mixture of expert models. We believe that while recurrent depth models are effective at learning reasoning patterns, mixture of expert models are better at storing and retrieving complex information. This suggests that a future architecture could benefit from integrating both approaches. In a standard mixture of expert model, each expert can only be activated once per forward pass or skipped entirely. In contrast, a recurrent mixture of expert model could refine its latent state over several iterations, allowing it to route to the same expert multiple times before switching to another. While mixture of expert models currently lead in implementing this type of memory in dense transformers, these ideas are also relevant for other memory mechanisms proposed for large language models.